Hey everybody. So today we're going to do lesson 2 on transformations, which will deal specifically with reflections. So reflections is one of those things you guys have been probably doing for a long time. They would have introduced the concept of a reflection probably way back in elementary. I don't know if you ever remember those cute little red mirror things where you would stick it on a piece of paper and then you would trace the reflection on the other side of the, I don't know. I had them when I was growing up, but anyway. Okay, so biggest concept that you need to understand when you perform a reflection. If I looked at myself in the mirror, my reflection in the mirror looks like it's the same distance inside the mirror to the mirror as I am outside of the mirror to the mirror. So if I was standing 5 feet away from a mirror, my reflection looks like it's standing 5 feet away inside the mirror. Okay, so it's always equidistant to the mirror line. Okay, so this is not in your book, just a quick definition. A reflection is a transformation where each point of an original graph has an image point resulting from the reflection of a line. A reflection may result in a change of orientation of a graph while preserving its shape. What we will look at is we're going to only look at 3 different lines of reflection. We are going to look at a reflection in the y-axis, a reflection in the x-axis, and a reflection in the line y equals x. Okay? Might as well think about this right away. If I was to reflect, I want to see, when you write tests and stuff, I want to see lots of like fish slapping hands right now. If I was to reflect, let's just pick on the x-axis for a second. If I was to reflect on the x-axis, I'm going like this, okay? I need you to see that that's a vertical reflection, okay? So we say it's a vertical reflection about the x-axis, okay? That can be confusing right at the beginning because we're saying the word vertical and we're using the letter x. And everybody's like, no, Hill, you got that wrong. No, you have to think visually. If I move vertically, I'm doing it against the x-axis. If I move horizontally, sorry, my hand was not set up to flip. If I move horizontally like that, okay, I'm actually doing a horizontal flip against the y-axis. Okay, so you got to be super careful about those guys. Okay, so consider the graph of y equals f of x shown below. Sketch the new graph of y equals f of x if the graph were reflected about the x-axis. Okay, so again, here's the x-axis. This is going to be a vertical reflection. Be sure to label all the key characteristics. How could you describe this reflection? What values would change, x or y or both? Are there any points that don't move when we perform this reflection? And what if we reflected it in the y-axis? So that's a loaded bunch of questions. You have the graph right below you. This is what the graph looks like. I just couldn't fit it all on one slide. So this would be a good time to pause me and actually try the reflection. Remember, just start picking points, and however far they are from the mirror line right now is this x-axis, however far away they are from the mirror line, they need to be that far away on the other side of the mirror line as well. So give me a pause, draw a picture, and then we'll come back together. Okay, so the picture that you should have should look like this, okay? And one of the things I want you to notice is what's happening to the points. Let's pick on the vertex here for a second. That was the point 1, 4, and it became the point 1, negative 4, okay? Let's pick on what's a nice friendly point that I could pick on for a second. Let's take a look at this point right here. 4, neg 5, well, it became the point 4, positive 5. So what I want you to notice is 2 things. Number 1, the x is not changing. Well, based on our conversation that we had yesterday, that should make sense because we said if I perform a vertical item, it should only affect vertical things, which is y, right? Doing a vertical item shouldn't affect a horizontal parameter. So what's happening is x is staying the same and y actually changes sign. If I was negative, I become positive. And if I was positive, I become negative. Okay, so we're going to try and go through each of these questions in turn. So here are some points that I've labeled. The first one was a description, which we would call this a vertical reflection about the x-axis. The second question was what values would change, X or Y or both, and we found out that it's only the Y's that changes. Are there any points that don't move when we perform this reflection? Yes, right here at -1, 0 and at 3, 0, those guys don't move. Now, there's a word for that, but first of all, mathematically, why don't they move? It's because the Y value is 0. And if I stick a negative in front to change the sign of 0, it's still 0, right? -0 is still 0, okay? So the points -1, 0, and 3, 0 do not change in the reflection. Now, the word I want you to start getting used to is right here, invariant points. An invariant point is a point that remains unaltered when a transformation occurs, okay? Okay, now, what if we reflected it about the x-axis? So again, let's pause me and then, sorry, not x-axis, y-axis. What if we reflected in the y-axis? We just did the x-axis. So now we're gonna go flip on the y-axis, which is gonna cause a horizontal reflection, but pause me for a second and see if you can come up with a drawing. Okay, so your drawing should look like this. And now if we started, we're gonna go through the same sort of list of questions here, but if we just started looking at some points for a sec, I have the point 1, 4, the vertex, and it turned into the point -1, 4. I have here the point 1, 0, and it turned into the point -1, 0. So what I want you to notice now is it's the x's that are switching signs, and it's the y that's not changing. Okay, so our description is a horizontal reflection about the y-axis. This time it's only the x values that are changing. The invariant point is at 0, 3. Okay, so this time the invariant point lies on the y-axis. Spoiler alert, the invariant point will always lie on the mirror line, okay? Okay, so let's think of these reflections just like we did with translations, where we talked about replacements. Remember the wording that we used yesterday? Yesterday it was like, okay, if I want to move 5 units to the right, I'm replacing x with x minus 5. Okay, so we're gonna have kind of a similar conversation going on here. So, whoops, sorry. Okay, to reflect the graph of y equals f of x about the x-axis, replace y with -y. Are there any points that don't move? If so, what are they? The invariant points are located on the x-axis, which is the mirror line, okay? Horizontal reflections to reflect the graph of y equals f of x about the y-axis, replace x with -x. Are there any invariant points? Yep, they are the ones that are located on the y-axis, okay? All right, now, this one we haven't actually talked about yet. To reflect the graph of y equals f of x about the line y equals x, what we do here is we actually just switch x and y, okay? So the point 2, 3 becomes the point 3, 2. Whatever was x is now going to be the new y, and whatever is y now becomes the new x, okay? Are there points that don't move? Yes, they are. Can you think of any sort of point that when I switch them, I get the same thing? Like 2, 2, or 8, 8, or -7, -7, or negative pi, or negative pi, negative pi, okay? It doesn't matter whether it's rational or irrational or whatever. If the x and y values are the exact same and I switch them, I still have the same point. So those are going to be the invariant points. Now, those happen to be all the points that lie on the line y equals x, which again, that's my mirror line, so that should make sense. Okay, so an invariant point is a point that is unaltered by a transformation. For vertical reflection, the invariant points will be on the line y equals 0, or if you think about it, the line y equals 0 is in fact the x-axis. For horizontal reflection, the invariant points will lie on the line x equals 0, otherwise known as the y-axis. And for a diagonal reflection, the invariant points will lie on the line y equals x. Okay? All right, so let's practice a couple things here. The graph of y equals f of x is shown. For each transformation of y equals f of x, complete the table. So first thing I'm doing here is I've replaced x with negative x. So if I've replaced x with negative x, we're doing a horizontal reflection about the y-axis. I've also written down my original domain and range here because I'm going to use that in a second to find the new domain and range. Okay, so I actually drew it first. So I took each one of these points here. I'm just going to circle them for you. This point, this point, this point, this point, and this point. And however far away I was from the mirror line, I went that far again on the other side. So I've got a horizontal reflection about the y-axis. Now, the image point, that's the mapping rule. XY would map to, well, what did we do? We made all my x's negative, so XY maps to negative XY. The domain, you can read the domain from the graph I've drawn, or you can just take a look at the original domain for a sec. The original domain was 0 to 5. All my x's get negative, so that's going to be negative 0. Well, negative 0 is still 0. And 5 would become negative 5. Now, remember that domain is always written smallest to largest. So the smaller number now is negative 5. So you'd go negative 5 to 0 now. Then the range wouldn't change because I didn't do anything to the y's. So it would stay as negative 1, 2. And the invariant points, yes, right here, the point 0, 2 remained 0, 2 in the new drawing. All right. So next guy, I replaced y with negative y. So now I'm going to do a vertical reflection, and I'm doing a vertical reflection about the x-axis. So I just stuck my negative in front here because we're kind of in front of the f of x. We're trying to get into this process of always writing things as y first because it's helpful in our head. We see things a little better when we always have that y by itself. So here's the drawing that you should have, okay? Remember that the x-axis right now is my mirror line. So however far any point was away from the x-axis, take a look at this little vertex here. I'm that far away on the other side of the mirror line for the reflection. So it's a vertical reflection about the x-axis. The domain for this, the image point would be xy comma x, xy maps to x comma negative y. The domain shouldn't change because I didn't do anything to x. But the range should flip. So this should become a positive 1 here, and this should become a negative 2. So negative 2 will be my starting number now. So it'll be negative 2 to 1. And then invariant points, I have 2 of them, 2, 0 and 4, 0. Okay, awesome. All right, then we're gonna try x equals f of y. Now, this is something a little new to you, but just take note, when you see x equals f of y, that's telling you that the x and y essentially have switched places. So that's your, hey, I'm doing a diagonal reflection here, okay? All right, so remember how we said, so first of all, let's, you're gonna take each point. So take a look at this guy. This guy here is 0, 2, so it'll become the point 2, 0. Remember we said we take each point and switch the x and y values. This is the point 2, 0, so it'll become the point 0, 2. Here is 3, negative 1, so it'll become the point negative 1, 3. 4, 0 becomes 0, 4, and 5, 1 becomes 1, 5. So when you plot those, you should get something that looks like that, okay? Now, I've stuck the mirror line in here because kids have a hard time seeing this as a reflection. And the reason you have a hard time seeing it as a reflection is because you're not orientating yourself to the mirror line. Take a look at this picture now, and I want you to tilt your nose so that your nose lines up with that line I just drew in. That's the line y equals x. And then you can see that it is, in fact, a reflection over that line. So it's a diagonal reflection about the line y equals x. The image point, well, the image point would be x comma y. Remember what I said, the x and y switch spots. So x comma y would map to y comma x, okay? The domain, these are kind of cool because the domain is just the old range, right? If everything x becomes y and everything y becomes x, the original domain now becomes the range, and the original range now becomes the domain. So my domain will be -1 to 2, and if you don't believe me, go take a look at it. Here is my left bound, and here is my right bound, and then the range becomes 0, 5. Here is my bottom, and here is my top. Okay, the invariant points are right here. There's only one of them. Remember that the invariant points have to intersect. It's not necessarily that they intersect with the original graph. They have to intersect with the mirror line. Okay, there will be lots of points that will intersect with the original graph that aren't actually unaltered points. They just happen to end up in a spot where the original graph was. Okay, so you're always looking at the mirror line itself when you're trying to figure out where the invariant points are. So in this case, it's 1, 1. All right, so a point, x comma y, lies on the graph of y equals f of x. State the coordinates of the image point for each of the following transformations. Describe in general what points would be invariant given each reflection. So the first one is a reflection about the x-axis. If I reflect about the x-axis, that's a vertical reflection. A vertical reflection, the equation for that is when I replace y with -y. So that would be y equals -f of x. The image point would be x comma y maps to x comma -y. And the invariant points would be located on the x-intercept. Y-axis, if I reflect against the y-axis, that's a horizontal fella. My equation would be, I'm replacing x with -x, so that'd be y equals f of -x. The image point would be xy maps to -x comma y, and the invariant points would lie on the y-intercepts. Then y equals x, the equation is x equals f of y. My image point is xy maps to y comma x, and the invariant point would be on any point that actually lies on that line, which is the line y equals x. Just a quick note before we move on from here, a diagonal reflection can also be represented by, I've given you x equals f of y, but it can also be called y equals f to the -1 of x. We're going to talk about that as a whole other lesson in a couple days when we do inverses. There are rules around when you can and when you can't use that notation. So for now, I just want to throw it at you saying, hey, this is coming, and it's going to be another talk we have in a couple of days. Okay. An invariant point of a relation can always be found on the line that the relation is being reflected about. It's always on that mirror line, okay? All right, the function f of x equals x squared minus x minus 6 is transformed. Determine the new equations. Now, I've given you g of x is -f of x. Okay, so you have to come up with a new equation. Again, though, take a look. Here's f of x. Well, f of x is x squared minus x minus 6. So all this says is, hey, I'm going to take that whole function and I'm going to put a negative in front of it. Okay, so let's do that. I take the whole function and I stick a negative in front of it. Well, now I'll just clean this up. This will be -x squared plus x plus 6. Okay, so this would be my new equation in terms of x. -x squared plus x plus 6. If I was to graph this guy and graph this, we would see that they're reflections of each other. Okay, so I've done that for you, just so that you can see the blue graph is my original and the red graph is my g of x. Okay? Okay, now this time though, this says, okay, take f of x, but every time you see x, replace it with -x. Okay, so every time you see x, there's an x, I'm going to replace him with -x. Here's an x, I'm going to replace him with -x, and then you're going to try and clean this up. Okay, so that looks like this. -x all squared would still be x squared. This would end up being plus x, and then this would still be minus 6. Okay, again, if I graphed these two, you will see that one is the horizontal reflection of the other. So the blue graph is the original, and the red graph is my new fella, my g of x. Okay? Okay, now, as we wrap up this note, we're just going to talk a little bit about combining translations and reflections together. And you must do the reflection before you do the translation. Okay, so when you're describing them, reflections have to be stated before translations. And then when you're doing it, reflections have to be done before translations are done. Now, we're going to do it all together with a mapping rule, but what you have to remember is the reflection is essentially multiplying by -1. So by order of bed mass, you do multiplication before you do addition or subtraction, right? So that's how the reflections always get done first. Okay, so the graph of y equals f of x is shown. For each transformation of y equals f of x, complete the table. So I've got y plus 1 equals negative f of x plus 2. If I was going to describe the transformations that occur here, and I would like you to pause me and write them down yourself, you should be writing 3 different statements. Go ahead and do that. Okay, and so the statements that you should read, first of all, I brought my 1 over, just so I had y equals by itself. And now I've got a vertical reflection about the x-axis, a horizontal translation 2 units left, and a vertical translation 1 unit down. Okay, now things I want to remind you of. I know I said this at our last lesson together, but I want to be a broken record for a sec to make sure you're hearing me. You have to write out the word vertical reflection, no abbreviations. I need to see that it's vertical. I need to see that it's reflection. And then I need to see about what line you're talking about, okay? All of that would get you like the full point there. Okay, so your image point. Well, x, y maps to something. What did we do to x? Well, I took it to the left 2. So that'll become x minus 2. What did I do to y? Well, first I switched the sign, so that's negative y. And then I brought it down 1, so that's negative y minus 1. Okay, my domain. Again, I'm going to take a look at this guy for a second. If I just back this domain up 2, I'm going to be looking at negative 2 to 3. My range, if I take this, we're going to do this number by number for a sec. So negative 1, flip the sign, that's positive 1, and then subtract 1, so that's at 0. 2, flip the sign, that's negative 2, subtract 1, that would be at negative 3. So I'm looking at negative 3 to 0. Are there any invariant points? One thing I want you to know right away, as soon as you throw in translations, you move everything left, right, or up or down, whatever it is, but everything changes. So as soon as you have a translation involved, there can't be any invariant points. Okay, so we just say none. Now, go ahead and get the drawing of this, but really, how I want you to draw it, like there's kind of two kind of thought processes out there to draw these. One is, okay, let's just deal with the reflection first, and let's draw what the reflection looks like, and then let's take that answer and move it to the left 2 and down 1. I want us to do it all in one step, and what I want to do is just pick the points, like this guy, and this guy, and this guy, which are the points where we change direction, and just plug them in to this. So this guy here is the point 0, 2. Well, if I plug 0 in for x, I come out with negative 2. If I plug 2 in, I get negative 2 minus 1, so that's negative 3. So 0, 2 would become that new point. Okay, so plot each of these new points and then reconnect the dots. Okay, so the picture that you should have gotten should look like that. Okay, and then you see each one of these guys. So this guy here, the 0, 2, became the point negative 2, negative 3. The point 2, 0 became the point 1, 0, and the point 5, 1 became the point 3, negative 2. Okay? Okay, now let's try this guy. A little bit of stuff we have to do here to clean it up. First of all, I want to divide both sides by negative 1. Then I'm going to have to add 1 to both sides. So your transformation equation that you should be looking at, kind of in more simplified form with y equals, should be y equals negative f of x plus 1. As far as your description goes, you should have 2 statements that you are writing. First of all, your vertical reflection, and then you're moving it up 1, so vertical translation 1 unit up. Nothing's happening to the x's, so the image point will be x comma y maps to x, comma, and then be negative y plus 1. Nothing's happening to the domain because nothing's happening to my x's, so that should still stay as 0 to 5. The range, again, just take each point and do the y stuff to it. So -1 with a negative in front would be 1, and if I add 1, that'd be 2. 2 with a negative in front would be -2, and if I add 1, that'd be -1. -1 is a smaller number there, so I say I go from -1 to 2. I've moved everything up 1, so there are no invariant points here. Okay, go ahead and try and draw it. And your drawing should look like this. Okay, excellent. All right, now this guy is a whole other conversation, and you need to listen very carefully to it. You cannot read transformations until you are in what I would call double factored form, and until that negative or double bracketed form maybe is a better way of saying that. Until that negative gets factored out of both of those terms, you're not ready to talk about transformations. Now, I want to tell you why. Remember that we're doing replacements here, okay? So, and remember that we have to do we have to do reflections before we do translations, okay? So let's just take a look at f of x for a sec. If the very first thing I was going to do was perform a vertical reflection, okay, well, that would involve me replacing x with -x. So that would look like this. Okay, now let's say now I want to go to the right, I don't care, 2 units. I want to go to the right 2 units. Okay, so now when I want to go to the right 2 units, I replace x with x minus 2. I'm not replacing -x though, I'm replacing x. So x is right here, and anytime you do a replacement, there's another set of brackets that get involved. So that would now say f of negative bracket x minus 2, because now I've replaced that x with x minus 2. And you can see then that when we're properly reading transformations, you end up with this double bracket system, okay? In this guy, there is not a double bracket there, which means I have to actually factor the negative out to see that double bracket before I'm ready to read the transformations off, okay? So that actually gets written like this. I took the negative out, and that left me with x plus 1 in the inner set of brackets, okay? So you have to be super careful of this. I promise you, your diploma will test you on your knowledge of whether you have that first coefficient factored out or not to read the transformations, okay? Okay, so the description of my transformations would be a horizontal reflection about the y-axis and a horizontal translation, 1 unit left. The image point would be x comma y maps to -x subtract 1 comma y. I don't need brackets in the mapping rule or the image point here because I do that negative. Like if I was to plug a number in there for x, it becomes negative, and then I subtract 1, right? That's what this x plus 1 is telling me to do. The x plus 1 is telling me to go to the left 1, and so that's why I see that here to the left 1. Mapping rules are always done exactly as the mathematics would want you to do it, and visually it tells you exactly what you're doing. There's no interpretation involved. Okay, so the domain, I'm just going to plug 0 into here, and I plug 5 into here to get my new endpoints. So I end up with -6 to -1. And then my range, well, I actually didn't do anything to the y stuff, so the range should stay exactly the same. The invariant points, I have moved everything to the left 1, so the invariant points, there are none of them. Okay? Good. I hope this is feeling okay. Here's what your picture should look like. I'm hoping you had paused me and drew that yourself. Good. All right, now, the graphs of y equals f of x and y equals g of x are shown. Write the equation g of x in terms of f of x. Okay, so what we're saying there is, ultimately, my answer should say, hey, g of x equals f of x after I do all this stuff to it, okay? So this is a transformation equation because it says in terms of f of x. This is not, we're not trying to have a graphable equation here. Rather just a way of describing the transformations that are occurring. So when you're comparing f of x to g of x, the first thing we're looking for is orientation. I would want you comfortable to say, hey, Hill, a vertical reflection has happened here, okay? I would also want you to be comfortable to say, hey, no horizontal reflection has happened. Because if a horizontal reflection had happened, this thing here would end up more like that on the new graph, okay? So all that's happened is a vertical reflection here. Now, once you establish that, you want to pick a point that you know for sure where it goes. I'm just going to pick on this point here because I'm pretty confident that that point has to turn into this point, okay? So we've established that there is a vertical reflection that has to occur. Now remember, the vertical reflections get completely dealt with before you talk about translations. So just do it and see where you end up. If I performed a vertical reflection on this, that point that I've circled down here would end up here. Now I need it to end up here. So now I figure out how much I have to slide it. So I have to go 1, 2, 3, 4, 5, 6 right, and 1 up. Okay, 6 right and 1 up. So I have a vertical reflection about the x-axis, and then I have a horizontal translation, 6 units right, and a vertical translation, 1 unit up. Now to come up with that equation then, that would look like g of x equals, the vertical reflection is my negative in front of x. Moving 6 to the right, I've replaced x with x minus 6. And then 1 up, I have a plus 1 on the end, which is the same as saying I've replaced g of x with g of x minus 1, but then I brought the negative 1 over. Okay. Good. Try this guy. Again, remember you're going from f of x to g of x. So you got to start over here. Deal with the orientation first. I want you comfortable to say, hey, a horizontal reflection has happened on this guy. So let's do the horizontal reflection with points that I'm comfortable with. I am comfortable saying that point will end up here. So if I just do the horizontal reflection, 1, 2, 3, 1, 2, 3, it would end up here. I now need to move it 1 to the right and 1, 2 up, 1 to the right and 2 up. So I have a horizontal reflection about the y-axis, and I have a horizontal translation 1 unit right and a vertical translation 2 units up. Okay, so that would become g of x equals the horizontal reflection, that's x gets replaced with negative x. Horizontal translation, x gets replaced with x minus 1 because I'm going to the right. But remember, that's a second set of brackets there. And then a vertical translation 2 units up, I have my plus 2 at the end. So this is what your final equation should look like. Now, this is usually the point where somebody's going to ask me, hey, can I just write this as negative x plus 1 and just simplify this? You can, it doesn't matter. In some ways, this is better just because it shows you all the transformations that are happening. But if this was like an equation that you would graph, by all means, you'd want to simplify things as much as possible, and then you'd want to distribute the negative, okay? But this is perfect as an answer. I'm totally happy here. Okay, just going to clear the ink, and there is what you're going to focus on. So give that a shot. Make sure you're practicing, make sure you're nice and neat with your drawings, and make sure you're thinking about this fully factored a second set of brackets inside the other set of brackets. Make sure you're thinking that through really, really carefully, okay? You know where to find me if you have any questions. In the meantime, have a fantastic day. Take care, guys.